before we move on for more exercises, I would like to review an important topics about short circuit effects of logical operators, namely conjunction and disjunction. So this topic will be very important for the understanding of the later exercises. This is something I would expect you to have already learned in the first year. So I'm just going to summarize the facts and do some quick exercises together with you, some examples. If you got any more doubts, you should really reach out to me or simply refer to maybe the 1022 Winter 21 lecture, which I referred to you in the beginning of the course for more information. But hopefully the summary I'm gonna review over here should be sufficient. Let's take a look. What's really a short circuit evaluation? Let's talk about conjunction first. And this is the so-called truth table for conjunction, right? So if I say some operand number 1 on the left, operand number 2 on the right, and both of them are Boolean expressions, and I'm combining them using conjunction, right? Ampersand, ampersand. That's for logical conjunction, okay? Logical conjunction. On the other hand, you can see for the vertical bar, it's for logical disjunction. And the way it works in terms of short circuit effects is very symmetric. So I'll talk about them one after another. So what about the short circuit for logical conjunction? It's based on the truth table that you should be familiar with. Let me review quickly with you. So we got operand 1 and operand 2. The only way to make the conjunction true is actually for both operands over here are true. If any one of them, for example, if any one of them, the second operand or the first operand is actually false, well, both of them are actually false. In that case, the result will just be false. Let me say it again. The only way to make the conjunction true is when both operands are true. If any or both of the operands are actually false, in that case, conjunction will just be false, right? That's the observation or like an insight into the truth table. So now, what does the short circuit effect really mean? It basically focuses on this these particular two rows over here. What if the first operand over here is already false over here? You can see over here. What if it's already false? Okay, so that's something I want to write over here. Okay, if I got operand 1 conjoined with operand 2, okay, if operand 1 is known to be false, does it really matter what operand 2 is? Apparently you can see it doesn't matter. In the case where the first operand is already false, the second operand here can either be true or false. Doesn't really matter because overall the result will just be false because at least one of the operands is already false. In that case, for the conjunction, the overall should just be false. All right. If operand number 1 is known to be false, it does not matter what operand 2 evaluates to, meaning that it can be true or it can be false, doesn't matter. Therefore, the evaluation of operand 2 in this case can be bypassed. And we're going to have a very similar argument for disjunction as well. I'll get to there in just a moment. Okay, let me just highlight what you should know here. So we talk about conjunction, and then if operand number 1 over here is known to be already false, in that case, it doesn't really matter what operand 2 is. Okay, operand 2 can just be bypassed. Okay, I think I meant to write bypassed. Bypassed. Okay. All right, so that's a principle. Let's look at one example. Okay, so this is some console application I just designed to actually illustrate, and I didn't really provide with you the source code. You can either follow me through the paper over here. If you really get it, good for you. But if you're not so sure, I would encourage you to type it out and also try it out. Okay, I will assume that you will do either way at the end. Okay, let's now take a look. We're trying to read in some integer x, read in some integer y, and then we'll do some checks over here to say x not equal to 0, and then y divided by x larger than 2. So the rationale is we are trying to do division. Every time you do division, you want to make sure you don't really run into division by 0 runtime error. So you want to make sure x over here should not be 0. Should not be 0. 0 to avoid division by 0 error. By 0 error. So you can see in this case, in order to really protect this particular expression over here, we are putting x not equal to 0 over here. Meaning that if this particular Boolean expression evaluates to false, meaning that x happened to be 0, in that case, we may just run into division by 0 example. Division by 0 exception, or division by 0 error at the runtime. However, because of the short circuit effects, if x happen to be 0, it is going to make this operand false. In that case, does it really matter what this is? It doesn't matter. So that means at the runtime, this execution will be bypassed. Okay, so that's a really important rationale, insight for you to keep in mind. Okay, so you can think about x not equal to 0 is so-called a guarding constraint. Guarding constraint for that division over there. Okay, let's now run through the example quickly. The first one, let's say x is equal to 0, y is equal to 10. So x would be 0 and y would be 10, for example. So now 0 not equal to 0 over here is going to be false. So it will basically, I'll put it here. So 0 not equal to 0, and also y will be 10, right? 10 divided by 0 larger than 2. Mathematically, you can see this one is really undefined, but now we're talking about programming. So what's going to happen at the runtime? At the runtime, we're going to evaluate from left to right, and this part over here is already false. And due to the short circuit effects of conjunction, this part over here is not even going to be evaluated. It will be bypassed. So in some way, we are bypassing this potential division by 0 evaluation. Okay, so that's the good thing about short circuit effects. So it seems the whole thing is just going to be false. The whole thing. So the whole expression over here is just going to be evaluated to false. Okay, meaning that we're gonna bypass this part over here, and then we're going to go to the else part. And because x is indeed equal to 0, so we're going to print out error division by 0. So that's actually the correct behavior. Okay, let's take a look at the second example. What about we got 5 and 10? If we got 5 and 10, in this case, we don't have no risk of division by 0. So we got 5 here, we got 10 over here. Okay, so now what's going to happen is, let me put it here. So 5 now, so you can see x is now 5. So 5 is not equal to 0, right? I'm talking about this expression here. And also, y would be 10. 10 divided by 5 larger than 2, right? What's going to happen? This part here is actually going to be true. 5 indeed is not equal to 0. And then if you got true over here, there's no short circuit, meaning that you're still going to continue with the evaluation. 10 divided by 5 is going to be 2. 2 larger than 2 is going to be false. So overall, it's still going to be false. Okay, and then we are still going to the else part over here. And then since x equals 0 is actually false, so we're going to print out this particular line, which is over here, y divided by x is not greater than 2. That's what we're going to have, right? So it's a very quick summary about what short circuit effect is, and then how it can be used as a guarding constraint over here in the case of protecting division by 0. Just go over this example and go over the definition and make sure you're okay. All right? That's about a quick summary of what you should know for conjunction, short circuit effects. Let's talk about the symmetric phenomenon for disjunction. Similar. Okay? Let's see what we should say over here. Okay, and which the way you can understand about disjunction is as follows. The only way to get false for the disjunction is when both operands are actually false. If either, okay, sorry, let me say it again. The only way to get disjunction to be false is when both operands are false. If either or both of the operands are actually true, in that case, the result will just be true. Okay, that's good. And what we are focusing on are these two particular rows. Okay, let me just highlight them. This one over here. And also this one over here. I want you to look at these two rows over here. These two. Okay, you can see for these two over here, the first operand is already true. In that case, does it really matter what the second operands are? It doesn't really matter because it will be true anyway. Alright, it's a kind of in a symmetric discussion as we did for the conjunction. So what we did earlier was about some observation for conjunction, and let's now do the same for disjunction. Let me write it down. Okay. Let me this one and this one over here. So we talk about operand number 1 or operand number 2. Okay. If operand number 1 is known to be true, as opposed to known to be false, right? In the case of conjunction, it's known to be true. In that case, does it really matter what operand 2 is? You know, it does not matter, right? It does not matter. What operand 2 is. Therefore, operand 2's evaluation is bypassed. Bypassed. Okay, let's now highlight the ones you want to pay attention to. We talk about disjunction. If operand 1 is known to be true, like over here, in that case, operand number 2 over here does not really matter, and the overall result will just be true anyway. Okay, so that's about the definition. Let's look at the example in a very similar way. So we still want to create some guarding constraint for the potential division by 0 runtime error. Okay, let's take a look. Let's say for the first one we got x being 0, y being 10, right? Let's now see what's going to happen. If I got x over here being 0 and y here being 10, okay, 0 and 10. So what I wrote is I say if x is equal to 0, or over here y divided by 10 larger than 2, right? So let's see what's going to happen here in this case, in the blue case. So x is equal to 0. 0 equals 0, or 10 divided by 0 larger than 2. Again, mathematically, you can see this one is undefined, but we are doing programming. We're always going to evaluate from left to right. Let's now do it. So if we evaluate from left to right, this part over here is going to be true, right? You can see now operand 1 is already true. Does it really matter what this part is? No, it does not matter. So which means its evaluation is going to be bypassed. We are not even going to evaluate it. Evaluation bypassed. And then the overall result is simply going to be true. Overall. Okay, overall is simply, okay, let me don't really block it. How about here? Okay, the overall result is simply going to be true. And of course, this part here is just true, right? For this one, it's really important. And you can think about this part over here is a guarding constraint. This x equals 0 is going to be the guarding constraint. Guarding constraint. And what I want you to really pay attention to is about how to define a guarding constraint for disjunction versus conjunction. Let me just draw your attention to this. In this case, the guarding constraint for the conjunction will evaluate to false to protect. And in this case, the guarding constraint for the disjunction will evaluate to true in order to protect the corresponding division by 0 error. Okay, that's something I want you to also think about. Okay, let's now move on with the tracing for the first example here. So we got 0 and 10. So it's going to be true. And so that means we'll go into this part over here, and then x is equal to 0 indeed. So we are going to print out error division by 0. So awesome. So that one is going to be correct. Okay, so error division by 0. Let's see the second input very quickly. So 5 and 10. Okay, so now we got 5 and also 10 over here. So now for this particular evaluation, what should it look like? Okay, let's now put it here. X will now be 5. 5 equals 0, or, and then 10 divided by 5 larger than 2. Okay, let's now analyze it logically. 5 equals 0 is going to be false. In the case of disjunction, if the first operand is actually false, we need to evaluate the right-hand side to really make sure what the result should be. For example, you can see in the case where the first operand is actually false, depending on what the second operand is, is going to be the corresponding answer. So you cannot just judging by the false alone. You want to see what the second operand is. So that means this will still be evaluated. So now, evaluating this, 10 divided by 5 larger than 2 should be false, as we saw before. So now you got the situation where, so this part over here, so this part here, false or false, is going to give you false. Okay, so that means false, meaning that we're going to bypass the entire if, right? So we're going to go to the else part over here, and then that one is going to say y divided by x is not greater than 2. Awesome, so that's the correct result. I'll let you study the program a little bit more carefully yourself, but I just want to walk you through the program quickly, right? So everything is available to you. It's up to you to see whether you want to just trace on the paper or you want to run it with a debugger on Eclipse. Let me just mention about one more thing about short circuit effects. Short circuit effects is very important to note. Let me just summarize quickly. So we got operand number 1 and operand number 2 versus operand number 1 or operand number 2, right? It's very important to remember the principle. Evaluation at the runtime is from left to right. That's very important. Evaluation at runtime is from left to right rather than simultaneous, meaning that we're going to evaluate operand number 1 over here. In case of conjunction, if that's already false, we don't bother with operand number 2. For disjunction, if this is already true, then we don't bother with this, right, as we said. Let's see this. So that means the order of arranging the guarding constraint is so important. So the consequence of this is the order of guarding constraint is crucial. Right, the guarding constraint, as you can see in the case of a disjunction, we put it first. And also in the case of conjunction, we also put it first. What if we put it as a second operand? What's going to be the consequence? Let's see. Let's just talk about this case where we might have some division by 0 error. Okay, let's see the first one, 0 and 10. So let's say, so now in this case, let's see what's going to be the output over here. So now y is actually 10. 10 divided by 0 larger than 2, and the guarding constraint, which is 0 is not equal to 0. Okay? And remember, evaluation is going to be from left to right. That's so important to remember. Left to right over here. If that's from left to right, let's see this. If you go from left to right, that means we're going to evaluate this. In that case, you will run into division by 0 error right away. It's more like an exception. Meaning that this guarding constraint is useless. Guarding constraint useless. Because even before you get to evaluate the guarding constraint, you already got the error. So that means the lesson, you should really always put the guarding constraint before the expression that you want to protect, you want to guard. Okay, like over here, right? You put the guarding constraint over here before the expression that you want to protect, for example, division by 0 error. Similarly, let's take a look at this example over here. The guarding constraint is over here, and we put it at the second operand. And this is the expression we want to protect against, right? Let's see what's going to happen here. So we are going to evaluate this again, right? X is 0 and y is 10. right? What's going to happen is, let me use a different color. So what's going to happen is 10 divided by 0 larger than, less than or equal to 2, or 0 equals 0, right? So x is 0. In that case, what's going to happen? You can see we're going to evaluate again from left to right. Let me use a different color just for fun. If we go evaluate from left to right, so now we're going to evaluate this one first. And that one also is going to give us division by 0 error first, before we can even evaluate the guarding constraint. Division by 0 error. And you can see this guarding constraint here is again completely useless. Given guarding constraint, useless. Okay, let me recap about this particular review session. You want to review the truth table for both conjunction and disjunction. You want to review the definition for the short circuit effect for both conjunction and disjunction, and you want to see an example where we put a guarding constraint first and how that can protect the division by 0 error in the case of conjunction and also in the case of disjunction. And you want to review this example as well, where we can swap the order of the guarding constraint to be the second operand for the logical operation. In that case, the guarding constraint is useless because the evaluation is going to be from left to right at the runtime. Alright, so that's about the short circuit effects for the logical operators I want to review. Make sure you really get it. If you don't get it, you may either want to reach out to me for more resources, or you want to ask me the questions during the Q&A, or just reach out. Alright, so we're going to do more exercises in the next part.